So the next speaker for today is Milap Kumar. He has attended level 2 this year of MTTS, and he's currently at ISER Bahampur. Are you a MSc student there, or can you introduce yourself, Milap?
Yes, sir. Like I am. Yes, sir. So I am an integrated PhD student, but it is equivalent to MSc.
Right.
For the
right.
first 2 years. Yeah. So it is.
Okay, good. And Milap will be talking about Rolle's theorem proved using nested intervals. Yeah, over to you.
Hi everyone. So I'll be talking about this theorem, Rolle's theorem. So I want to ask that how many of you all already know the proof of this? That have you seen the proof of this? Like some other proof? Anyone? Yeah, you can just unmute and say. Okay. So I will prove this using nested intervals. So I am going to first assume that if you have a continuous function like this from some closed interval a comma b, and you have some continuous function such that fa equal to fb. Okay, fa equal to fb. Then I will construct a sequence of nested intervals. So some a1 b1 inside this, some a2 b2 inside this, in such a way that such that the diameter of these intervals will go to 0. So in the intersection there will be exactly one point. So I will call that point C, and then I will prove that f dash at that point is equal to 0. Okay, so first I will construct this sequence. So how are we going to construct this sequence? So proposition 1. So proposition 1. So let f be a continuous function. So let f be a continuous function from closed interval AB. Then closed interval is such that fa equal to fb. Then there exists another point C and D inside AB. So sorry, inside A2 A plus B by 2, or instead of this interval, I can also take A plus B by 2 to B. Here close and here open. I will explain why this happens. So there is some C and D inside this such that this length of C minus D is equal to B minus A by 2, and f of C equal to f of D. So see, if you have a continuous function A to B here, now I want some other points here such that on these two endpoints also the function value are same, and the distance between this is half of this distance. Okay, so how can I construct? So we can see in this manner that if I cut this in the half, A plus B by 2, and if I translate this here, then it will be something like this, and this is the point that I want. Okay, so how can we show this? So if the statement is clear, then I will write the proof now. So let me. So here I just write that statement. So here I just write that figure again so that you can see. We have given that fa equal to fb, and we want to get some C and D such that this condition happens, and C minus D is B minus A by 2. Okay, so proof. So proof is that that you construct this new function, right? So like we translated this. Okay. So first we cut in half and then we translate this. So we construct a new function g from a to a plus b by 2, a to a plus b by 2 to r, such that g of x is f of x. See, here you can either translate this to here or you can also translate this to here. It will give you the same thing, okay? So here, so first f of x minus f of x plus b minus a by 2. So b minus a by 2 is this is the length, okay? So now you see, so since f is continuous, so this is also continuous, so this is also continuous, so this implies that g is continuous.
Powering on.
So this implies that g is continuous. Now I am going to use that intermediate value theorem. Okay. So g of a is f of a minus f of a plus, so this will be a plus b by 2, and g of a plus b by 2 is f of a plus b by 2 minus f of, okay. So here it will be f of a plus b by 2 upon a plus b by 2 minus b plus a by 2. So b minus a by 2. So this will be, so a by 2 gets cancelled. So this is f of b, and f of b equal to f of a. So if we assume that f of a and f of a plus b by 2 are not equal, so I am assuming, but then I can show that even if we don't assume that, then also this will follow. How? So that I will tell you later. For the time being, assume that f of a is not equal to f of a plus b by 2. Okay. Then g of a and g of a plus b by 2. So these two have opposite signs. So there exists some c, right? So there exists some c inside where? So c inside this, right? Inside this a2, and inside the open bracket a2 a plus b by 2, such that, so this is by intermediate value property, g of c is equal to 0. So g of c is what? F of c equal to f of c plus b minus a by 2. So now I will call this element d, okay? And since c is inside a to a plus b by 2, and I am just adding b minus a by 2, so this will also imply that d is inside a plus b by 2 to d, okay? So I will call this element to be d. Hence I have get fc equal to fd and such that d minus c is, so d minus c is what? B minus a by 2. Fine, done. So if I have some points, if I have a continuous function, and if I have at some 2 points, if the function value are equal, then I can get another 2 points inside that, strictly inside that, in such a way that this distance will be cut in half, and again at that 2 points the function value are also equal, okay? And now I can do this thing again and again, okay? So in this way I will have a sequence of nested intervals. So if I do this again, then what will happen? So a and b, then I will get again a1 b1, then again if I apply this thing, then I will get a2 b2. Okay, now I will come to this, that why it is enough if I don't. So suppose that fa equal to f of a plus b by 2, okay? So suppose if fa equal to f of a plus b by 2, then like already we have 2 points, a and a plus b by 2, such that distance between a and a plus b by 2 is what? B minus a by 2, right? And then I can choose my interval, either this interval or this interval. So if so, I can choose either this interval and this interval. So in this case also, I have a sequence of nested intervals. So if I will call this to be my A1 and this to be my B1, and then I can do the again same thing here. Okay. So is it fine? Or like if you have any doubt, then ask. Okay. Okay. So
yeah, any questions from the audience so far?
Yeah, if you have any question, then ask.
So Milap, what exactly you did just now is like you have constructed a sequence of nested intervals, right?
Yeah. Yeah.
And what is the property of that sequence of nested intervals? That
So property is that suppose that this sequence of intervals Jn, An, Bn. So it has the following properties that f of An will be equal to f of Bn. So this is the first property. The second property is that Bn minus An will be B minus A by 2 raised to n, because I am cutting it in half again and again and again. So this thing will come, and I am also making sure that at the end points the function value are same. Okay.
and finally, what do you want to prove with this?
So with this, if I have a sequence of nested interval theorem, then sorry. So if I have a sequence of nested interval, then and in such a way that if Bn minus An converges to 0, okay. So in this case, Bn minus An will converge to 0. Then there exists at exactly one point C, which is in the intersection of all these intervals, right? And then I will prove that at this point f dash will be 0. At this point, the f dash will be equal to 0. So I will prove this.
I see. Okay, please proceed.
Okay. Okay. So now, okay. So by this proposition 1, I have a sequence. So I have a sequence of nested intervals. We have sequence of nested intervals with the property properties that I just told, f of An. So I just quickly write the sequence of natural. So I will call this sequence to be Jn. Okay. So these are Jn, An, Bn. So okay. Now by using nested interval theorem. So by using the nested interval theorem, I know that. So here see. So Bn minus N. So this converges to 0, right? This converges to 0. So like geometry, it is also easy to see that if you have sequence of nested intervals such that if the endpoints go to 0, like if the difference of their endpoints go to 0, then there can only be at most one point, and this theorem says that there is exactly one point. So I will call that point C. So using this nested interval sequence, we have C equal to intersection of all these Jn's and N. And also in this case also we have An will converge to C and Bn will converge to C, and here I have C, here I have Ans, and An will be less than C, less than Bn, right? So here are A1, A2, An. So this will converge from this, B1, B2, Bn. So they will converge from this, and we have exactly one point C. Now suppose okay. So now, do you know that if I have two sequences, okay, so now I will prove that f of Bn minus f of An upon Bn minus An, this will converge to f dash C. this has to converge to f dash c. There is no other choice. So if I prove this, then I am done. Okay, is it fine? Because if I prove this, then see, f of bn equal to f of an, right? So this sequence is nothing but just simply zero sequence. So zero sequence converges to f dash c. Then this c has to be what? Then f dash c has to be equal to 0. Which is fine. So now it is enough to just prove that this sequence will actually converge to f dash c. And geometrically we can see this in this way. So at each end, I am looking at the slope of this secant line. So here it is A1, here it is B1. So first I am looking at this line, and then I am looking at this line, and then I am looking at these lines in such way that this one point is in this side of C, and the other point is in that side of the C. So slowly this will converge to f dash C only. The slope of the slope of the tangent at C. Okay. So now I will prove that this is actually equal to that this will converge to f dash C. Okay. So for this, I'm going to use some not like it is very easy to prove that suppose you have some sequence alpha n by beta n that converges to some number gamma, and you have some sequence alpha n dash by beta n dash that converges to gamma, and also if beta n and beta n dash are positive, then alpha n plus alpha n dash upon beta n plus beta n dash will also converge to gamma. Sir, can I prove this, or like do I have enough time? Like it will be just 2-line proof, but
yeah, please finish within 1 or 2 minutes.
Okay. Yeah. So okay. So my aim is just this. So this is my aim now. So like first I will just take some epsilon positive, and I will show that this distance between this is less than epsilon. Okay. So first choose some epsilon. Okay. So if I choose some epsilon, then since this sequence converges to here, so I will get some n1. This sequence converges to here, so I will get some n2, and then I will choose n to be the maximum. And for that point onwards, I will have alpha n by beta n minus gamma. Okay. So like why I am doing this, so that you will see. Okay. So this thing, why I am doing this, so you will see this afterwards. So this will be less than epsilon, and also alpha n dash by beta n dash minus gamma is less than epsilon. So this means what? This means what? That alpha n by beta n minus gamma is less than epsilon by. This means that alpha n minus gamma beta n is less than epsilon by beta n, and alpha n dash minus beta n dash gamma is less than epsilon beta n dash, because beta n and this beta n dash are positive, so that's why I can just take them here. So now it minus epsilon by beta n, alpha n minus gamma beta n is less than epsilon by beta n. So I'm just expanding this. Now just add these two. Now if I just add these two, then I will have this. Right. And again, since these are two positive, so that sum is also positive. So now I can take back. So if I take back, then from this will come for all n greater than equal to maximum of this. Hence, I have proved that this sequence converges to the same gamma. So okay. So is the proof clear? So I have proved that if I have two sequences, alpha n by beta n, which converges to gamma, and alpha n dash by beta n dash, which converges to gamma, and also if beta n and beta n dash are positive, then alpha n plus alpha n dash upon beta n plus beta n dash will also converge to that same number gamma. So now how can we use this? See here, an converges to C and Bn also converges to C. Now an converges from left and Bn converges, so and this Bn converges from the right. So now and we know that, okay, and since f is differentiable on this open interval a comma b, so in particular f is differentiable at this point C. Okay, so since f is differentiable at this point C, I have f dash C equal to what? Limit of x tends to C, f of x minus f of C upon x minus C. And we have also that if a function is continuous at some point C, then if I take any sequence xn converges to C, then this will imply that f of xn will converge to f of C. Okay, and since f is differentiable at this point C, so this means that for this sequence, if I choose this sequence, since here x tends to C, so if I choose this sequence an which converges to C, then this implies that f dash C is f of an minus f of C upon an minus C. Now I think I will rub this part. And similarly, Bn converges to C, so f dash C is f of Bn minus f of C upon Bn minus C. And now like can any one of you just tell that how to do now from here? Now it's easy, right? Now see, here an is less than C is less than Bn. So if I want to use this result, then I will have to make sure that these things are positive. Okay. So f dash C is nothing but, here it will be, sorry, this is limit n tending to infinity. So like this converges to C and this also converges to f dash C. Now, so f of an minus f of C. Now here I want to make sure that this thing is positive. So now an is less than C, so I'll just swap these numbers. So it will be C minus f of C minus an. So I will have to again swap here. So it will be f of C minus f of an. So this converges to f dash C. And now f of Bn minus f of C. Now this thing is already positive. Bn minus C is already positive. This converges to f dash C. Now by this result, if I just add these two, then I will get, now you have to add this and this. So f of an, so f of Bn minus f of an, and I have to add these two. So Bn minus an. So f of Bn minus f of an upon Bn minus an. This will converge to that same number. So f dash C. And now since f of an was equal to f of Bn for each n, we have this zero sequence which converges to f dash C, and hence f dash C equal to 0. Okay. So the proof is done, right?
Yeah. Nice. Thank you, Milap, for the nice talk. Any questions from the audience? Quick questions.
Yeah, if you have any question, then you ask. I'll be happy to help. So like this proof is not very standard proof. So like you that like by that I mean that in the standard textbook, so this proof is not given. So I was doing this as Kumaran sir's book, and from that in that book, so there was some exercise that said that if you have FA equal to FB, then prove that there exists some C and D such that this thing happens. So from that exercise, I got an idea that if I have some other points, then I can just do this again and again and again. And from that, I got this idea of this proof. Okay. So if in case of no questions, thank you.